You are about to find out that your kettle is a national security risk, not to you, to everyone else. The moment you flick that switch, something enormous, hundreds of kilometers away, has to spin slightly harder within seconds, or the lights begin going out. And the entire country only carries about 3 seconds of slack. Here is the strange thing about electricity. Almost none of it is stored. The power arriving at your wall socket did not exist a moment ago. It was made somewhere else in the fraction of a second it took to reach you by something turning. Sit with that for a moment. Not a warehouse, not a tank, a machine, mid-rotation, matching you right now. That machine is called a synchronous generator. Strip away the jargon and it is a giant magnet spinning inside a ring of copper. Steam, falling water, burning gas, or wind turns the magnet, and the turning pushes electrons back and forth along the wire. In Europe, Australia, most of Asia, and Africa, it turns 50 times every second. In North America, 60. That number has a name: frequency. Now, here is the part almost nobody knows. Every large generator on your grid is spinning in lockstep, not roughly, exactly. Thousands of machines spread across thousands of kilometers, magnetically locked together as though they were gears inside one impossibly large engine. Nobody forces them into step with a cable or a signal. The physics does it. Pull one slightly out of alignment and the others drag it back. So what actually happens when you add your kettle? You slow the whole thing down by an amount too small to measure. But your kettle is never alone. Millions of switches flick on and off every second, and the shared rotation feels all of them at once. When demand outruns supply, the grid slows. When supply outruns demand, it speeds up. Frequency is not a technical footnote. It is the speedometer of an entire civilization, and it tells a control room the balance of a nation in a single number. Which raises the obvious question: how much room is there before that number becomes dangerous? Less than you would hope. The only true buffer is the kinetic energy already locked inside those spinning masses. Engineers measure it in seconds, using something called the inertia constant, which asks a simple question. If all the fuel vanished this instant, how long could this machine keep delivering full power on momentum alone? For a typical generator, the answer is a few seconds. Stack up an entire grid and you get roughly the same answer. Everything beyond those seconds is not physics. It is reaction. So the grid defends itself in layers. The first layer is free, momentum. Heavy metal refuses to stop instantly, and that stubbornness alone buys the system its first few seconds. The second layer is mechanical. Governors on the turbines sense the slowdown and open the valves. That takes seconds. The third layer is human and commercial. Reserve plants and batteries are paid to stand by and inject power on command. That takes minutes. And the fourth layer is the one nobody likes to talk about. If frequency keeps falling, automatic relays deliberately switch off entire neighborhoods. Not by accident, by design. The grid amputates part of itself to save the rest. You can watch all 4 layers fire in a single real event. On the 9th of August 2019, lightning struck a transmission line north of London. The line recovered in under a second, exactly as designed. But in the disturbance that followed, the Hornsea 1 offshore wind farm and the Little Barford gas power station both cut their output, and Britain lost around 1,500 megawatts in seconds. Frequency fell through the safety floor to 48.8 hertz. The automatic relays did their job. Roughly 1 million customers lost power, and the rail network seized up when trains that had detected the dip refused to restart without an engineer physically on board. The technical report published afterwards by National Grid ESO laid out the sequence minute by minute, and the regulator, Ofgem, ran its own investigation. Nothing exotic failed. The system simply ran out of seconds. And those seconds are getting shorter. Solar panels and most wind turbines do not have a heavy magnet locked to the grid's rhythm. They connect through inverters, which are essentially very fast electronic switches. Clean, efficient, and almost weightless in the way that matters here. In 2018, a group of power system researchers, including Federico Milano, Florian Dorfler, Gabriela Hug, David Hill, and Gregor Verbeek, published a paper laying out the foundations and challenges of low inertia systems. Their point was blunt. As spinning machines are replaced by electronics, the grid's momentum falls. Frequency moves faster after a shock, and control schemes designed for a slower world may simply not react in time. Engineers are answering with synthetic inertia, batteries programmed to imitate the physics of a flywheel, and with real flywheels spun up purely to add weight back into the system. But the underlying problem is not going away. The buffer is shrinking, and when the buffer runs out, systems fail in a very particular way. On the 14th of August, 2003, a power line in Ohio sagged into an overgrown tree. Ordinary, forgettable, except that an alarm system had silently stopped working, so the operators watching that region did not know. Load shifted onto neighboring lines, which sagged, which tripped, which shifted load again. The final cascade tore across the northeast of the United States and into Ontario in a matter of minutes. Around 50 million people lost power. The joint United States and Canada Power System Outage Task Force spent months reconstructing it, and their final report reads less like an engineering failure than a chain of small omissions arriving all at once. 3 years later, on the 28th of September 2016, storms tore transmission towers out of the ground in South Australia. Repeated voltage dips caused several wind farms to reduce output because of protection settings nobody had examined closely enough. The interconnector to Victoria took the strain, overloaded, and disconnected. An entire state went dark in seconds. The Australian energy market operator published a detailed final report on the event, and one of its clearest lessons was that the grid had behaved exactly as its settings instructed. The settings were the problem. There is one last detail, and it is my favorite, because it is the only time this hidden system ever becomes visible to ordinary people. In early 2018, clocks across continental Europe began running slow. Oven clocks, microwave clocks, clock radios. They lost around 6 minutes over several weeks. Those clocks did not have their own timekeeping. They counted the pulses of the grid, 50 a second, and trusted it completely. A power imbalance in the Balkans had dragged the average frequency down by a fraction of a hertz, and every counting clock on the continent quietly fell behind. Nobody lost electricity. Nobody noticed anything except the time. That is the closest most people will ever come to seeing it. Because this system's greatest achievement is that you have never once had to think about it. Not the lockstep, not the seconds, not the 4 layers standing between your evening and darkness. Somewhere right now, there is a room full of people watching a number hover around 50 or 60, adjusting a continent's output to match a country's habits, guessing when a nation will collectively decide to put the kettle on. So flick the switch. Go ahead. Your kettle was never a national security risk. It is a request sent instantly to every spinning machine in your country and answered within 3 seconds, every single time, by an engine so large and so quiet that you have spent your entire life inside it without ever once hearing it turn.